So welcome back. Now we start recording. Welcome back to the second week of statistical modeling. And well, I hope that you regularly check what is in the issues, because that's where the interaction takes place. So there was a new version of FSTA, and then this new version now has the auto-completion. And in this case, we have to thank the student Giacomo Boschi, who wrote the auto-completion, because here there is a variety of persons. There are persons who are already outstanding. So now, if you this menu automatically appears, right? And the auto-completion is very important because you do without looking at the help. Is very, very important. So if you want to write the auto-completion for certain functions, you talk to him or to her, and then we will publish the video so that with the details, so that it can be useful for anyone. So therefore, the idea is, if you want to be involved in the FSTA project, start doing something through the pull request, and the pull request will remain in your CV. So try to take advantage of this chance. Now there will be a very important firm of Bologna who is looking for young programmers. And I've told him that, look, that now I have the best in the world of my students. Okay, well, but this is a financial firm. Financial firm which operates at Prometheus called. It operates at European level. Therefore, this is the chance that you certainly have to exploit. Right. So when in the future, when you are very rich, then I will still be professor of statistics, then you'll come to me, then, okay, you'll pay me a coffee. Okay. Now, about the issues. So there is a new version of the book Data Science with MATLAB. Therefore, those who already had the book now can have access to the updated version. Therefore, the page of errata corrige now is blank. Of course, this does not mean then that it should be blank, because it could be that there are additional typos or everything. So keep pointing out and signaling mistakes that you find, or maybe also things that you find unclear. Sometimes when you write something, maybe it is clear for you, but it may not be clear for another person. So we have, the job of a teacher is a job where, unless you think you are God, you have to improve every time. So this is our, if you want to do a fair job. Also, thanks to Samuele 7F who asked this clarification. Okay, the new book, Statistical Modeling, will appear next week in the Giapichelli website. Okay, now, first of all, we are doing a summary of principal component analysis in order to recall what we have done last week. Then we will do the correction, and then we will move along. So, steps of principal component analysis. Well, generally the variables are on different scales, on different units of measurement, therefore you have to standardize the data. So you have to work on the variance covariance matrix of the standardized data that is on the correlation matrix. The total variance of the correlation matrix, the sum of the elements in the diagonal, in the main diagonal of the correlation matrix, is P, if there are P variables. This is the variance that you want to explain. You want to explain the variance of these P variables with a smaller number of variables. These variables, the smaller number of variables, are obtained as a linear combination of the original variables. And they are orthogonal. So the necessary condition for correctly applying principal component analysis is high correlation. That is, if you have a three-dimensional data, it is true that this data are three-dimensional, but the dimension is one. It's just one line. Okay, well, the points are not exactly on a line, but that's the difference between mathematics and statistics. For a mathematician, the points are not on a line, and you cannot do anything. For a statistician, you try to approximate. You try to see how much the line can approximate the variability of the points. So here, this is a typical example of data in just one dimension. And on the other end, this is a typical example of data in two dimensions. Right, so here there are two dimensions. The third is very small. Of course, if the data are on a ball, you cannot do anything. You cannot reduce the dimension because there is not a dimension which is much larger than the other. So here, so therefore, check the correlation. Check the correlation. Compute the total variance which is explained by the components, therefore compute the eigenvalues, compute the cumulative percentage of the total variance which is explained. How many components? Because you start from P and then you end up with K. K much smaller than P. How many components to retain? There are several criteria. One criteria is that you have to explain at least 0.95 for each variable. So it's compute this number, 0.95 to the P. Then you stop when your K principal components explain a total variance which is greater than this number. Or if the variables are standardized, use the eigenvalues which are greater than 1. Because the variance of each variable is 1. And therefore, an eigenvalue which is greater than 1 means that you explain at least a little bit more than one variable. So this is a safe criterion. Or, you want that the explained variance can be at least 60%. These are minimum requirements. What is the best? No one knows. These are sensible criteria. Therefore, now you compute the variance explained in order to have an idea of the goodness of your analysis. Then you check what are the correlations between your original variables and the principal components. Right, please.
In our case, are we going to use the standardized data?
Well, I will this is in my next slide. Yeah, so the question is, when do we use standardized data, or on the other end, when do we just work on mean deviations from the mean? That was your question. I'm going to address it in 1 minute and 40 seconds. Right. It was on my radar. It was on my list of things. Yes, you have anticipated me, but absolutely, your question is absolutely pertinent. That I'm going to address it in shortly. So therefore, check the correlation. Check the correlation because you have to interpret. You have to understand what is the meaning of the first principal component, which are the characteristics of the units which have large values of the first principal component or of the second principal components. For example, in the map of the Italian provinces, you have to find the quadrant, the portion of the space where are the richest provinces or where are the poorest provinces. So, then, check the commonalities. The commonalities are the proportion of variance of each variable, which is explained by the K component. It could be that a variable is fully explained by the first principal component, so the angle is very small. or it could be explained by the second principal component. That is, each variable has a variance, which is equal to 1. The correlation, the sum of the squares of the correlations of each variable with the principal components is the communality. Communality greater than 0.95 means that your variable has been explained in a very good way by the K principal component. So assess the exploratory power of the model for each variable. So you check what are the variables which are best explained and which are those which are worst explained. Then you compute the scores, the score for each unit. These are the scores. A matrix which is n times k, generally a matrix which is n times 2, because you stop with the first two principal components. This matrix maximizes the total variance, represents the best k-dimensional subspace for the projection, minimizes the sum of the squares of the orthogonal distances, and minimizes the sum of the squares of the residuals, as we have seen using the SVD. So it's incredible. Several criteria, you end up with the same result. This is really very, very nice. You start with A, with B, with C, but you end up with the same conclusion. Now, let us come to your question. When do we start from S, deviations from the mean, data not standardized, or when do we start from R? Do we compute the eigenvalue of S or of R? Do we work with deviation from the means, or do we work with standardized zeta scores? Well, you do not standardize the variables just when the orders of magnitude of the variables is not too different. There is no intention to eliminate difference in variabilities, because with standardization, you work with vectors which have the same length. They have the same variability. Yes, you start with variables that are on equal footage, that is, have the same variance. On the other hand, sometimes you don't want to eliminate the difference in variability. For example, the variables are percentages. They all already are in between 0 and 100. Or it could be that you have territorial index number. For example, you have that the average is 100, then you have 120. This means that in that particular region, the value is 20% greater than the average. This is or you have ratings. All the variables are on the same scale, from 1 to 10. All variables on the same scale. Apart from this example, you always work with standardized variables, right? So if you are in doubt, you work with standardized variables. Therefore, our function PCAFS, if you do not specify anything, does automatically the standardization for you. PCAFS, right? Automatically. There is an option which says standardization, which is true or false, but the default is true. Therefore, in the exam, if it is explicitly specified, you do not work with standardized variables. Otherwise, in all the other cases, you standardize the variables. Right. Okay, then, so we talked about the correlation between the variables and the components, which are represented by arrows. We talked about the scores, and then there is a joint representation of the scores and of the correlation. And this is called Biplot or Biplot. Now, it is time now to go to the correction of the file woofer. Okay, so, you know, these are the first things that I usually do. I define the end, the height of the metric of the table xt, then the v names, and generally row names are names and v names. This is always valid, that you always have n, and then if you also need p, then you take the number of columns of your data matrix. Right, okay, so after running this, so in the workspace, what you get is n are names, and this table, right? Oh. So the represent data using parallel coordinates, and then using parallel coordinates, and then you want to put in the first line, you want to put the names. The names, so you add advars. You could do it also manually, but advars is the professional way, this function that adds these, you see this xt that has 3 columns. When you run this thing, xtt has 4 columns. So you have added these are names in the first column. Right. So before one means before, in which position do you add the variable? You add it on the left as the first position. And then you do the parallel plot. Parallel plot. Okay, then you have to know that you can drag them. Did you pay attention that you can drag, you can change here the order of the variables? Right. Okay, what do you see here? Actually, I don't see anything at all, to be sincere. I just see a bunch of lines, but it's not very clear to me what to think and what to comment, to be fair. Then construct the scatter plot matrix with the univariate boss plot on the main diagonal, and then background color. Background color true, and then you end up with this background color and then the boss plots on the main diagonal. Therefore, the background color reflects the correlation. If the background color is blue, the correlation is positive. If the background color is red or reddish, the correlation is negative. The amount of reddish depends on the strength of the correlation. Well, actually, you will expect that thickness, length, and width should be much more correlated. On the other hand, the correlation is a bit loose, is a bit small. This is the first comment that comes to your mind. So there is a univariate outlier, positive correlation between length and thickness. Yes, here, positive correlation. Not very strong, but a positive correlation. Width and thickness are not correlated. Width and thickness, you can see the background is very, it's almost non-existent in the background. So therefore, here you had to comment in terms of the angle. If two variables are not correlated, therefore their angle is 90 degrees. If two variables have a strong negative correlation, the angle between the vector is close to 180 degrees. Right. The variables are very strongly correlated, the angle is very small. Right. Compute the correlation matrix, okay, core, and then array to table here, nothing, what can I say, yeah. So therefore, what do you observe? This positive correlation between thickness and length, thickness and width, as we saw before, they have virtually correlation which is virtually zero. Now discuss the implication of the statement. For each type of offer, the proportions among the three measurements are fixed. If these were true, what will be the correlation matrix? What will be the correlation matrix if these were true? Full of ones. Perfect correlation between each pair of variables. Right? Well, you want to see it. X is equal randen, for example, 1000,1. And then you do x TMP is equal to x times 6, x times 12. Okay? So 3 variables. Core of x TMP is a matrix of 1. It's a 3 by 3 matrix of 1, clearly. And this is what you expect if the proportions were fixed. Now, and on the other end, if you have something like this, the correlation is what? If you have something like that, I remove the constant. Nothing changes. Nothing changes. Core XTMP. Okay. Now, if I do this, minus 3, if I multiply it by minus 3, then the correlation is what? The correlation is what? But which number? Minus 1. Right. Okay. Okay. The third variable is a negative correlation. Okay. If instead one of the measurements were out of control, then its correlation with the other variables will be close to 0. So in other terms, in geometrical terms, if the correlation is 1, the data lie on a straight line. They are 3D but lie on a straight line. Right. The data are one-dimensional. Now, performance dimensionality reduction. Discuss whether in this context it is better to work on the covariance or on the correlation matrix. And this is just what I mentioned before. In doubt, we standardize. Right. Unless it is explicitly said, we standardize. Now, write the condition and the equation that the eigenvalues must satisfy on the correlation matrix. Okay. The correlation, the condition, you agree that it is this condition, right? This is a polynomial of third degree if there are 3 variables. If there are 6 variables, this is a polynomial of 6th degree. 6th degree, there are 6 solutions by the fundamental theorem of algebra, right? So, the solutions that are found by the computer. When 30 years ago, they forced me to solve this third degree equation, but then you had to try +1, -1. I don't know if you ever tried or they forced you to solve this. That was really very, very annoying. Now, fortunately, we can concentrate on the most interesting things and not on this computation that are done by the machine. However, so therefore, the eigenvalues, they come from the solution of this equation. Degree 3, and so you have 3 solutions. Or you do it in symbolic term. Well, if you do not want to do it in symbolic term, you do char poly the function which computes the characteristic polynomial. This is the coefficient of the polynomial equation, written, but it's much better to write them in a symbolic way. This 1, minus 3, 2.46, 0, minus 0.49, you see, without the symbolic. And then you have to compute the roots. So you have to compute the roots, and then therefore here you do roots. Okay, and these are the roots. What is the sum of the roots? What is the sum of the eigenvalues? Here, how many variables there are? 3, and therefore it is 3. Right. So the sum here is 3. Right. Therefore, 1.7688 divided by 3 is the proportional variance, which is explained by the first principal component. Right. So in symbolic term, you have this symbolic variable, and then you transform A in symbolic, and now look at the symbolic representation of the correlation matrix. Don't you think it is a ridiculous representation, isn't it? But this is what the machine does, how it represents the number. But they are true. If you do with the calculator, then you get the numbers that you have found in the correlation matrix. Okay, then you do same function, but here you work with in a symbolic way. So this is this is the polynomial in third degree. These are the things that the machine does, multiplied by square root of 209, multiplied by square root of 709. These are, well, unfortunately there is this VPA which controls the number of decimal points. And the number of decimal points here is, right, VPA. So you write in a much easier, much understandable way. And then what you do, then you solve, and then you solve, and then you find the roots. VPA also you control the output. Roots. Right. Did I miss something to launch here? Let me see. Let me try to launch everything up to this point. Up to line 53. To line 53. Okay, remove the breakpoint. Stop, and then display. Okay, these are the roots. Okay, show the percentage of variance explained by the different components. Okay, here you can do things manually. We have done last time. So you have the correlation matrix, you compute the eigenvalue, then the eigenvector, and then so on and so forth. Or otherwise, you call PCAFS, and now you have the completion. Now you call just PCAFS with just options Biplot is equal to 0, and then plots is equal to explained. Therefore, now if you do PCAFS XT, and then when you do plots, probably I do not have the latest version, because if you have the latest version, these plots automatically comes out thanks to his work. So it was my absolutely my fault okay, yeah, PCA XT, right, PCA FS XT, no, plots, okay, no, it was not my fault. I wanted to see why they didn't not come out. In fact, there was not a reason. I was confused because I was sure to have the latest version. So if you have the latest version, the auto-completion must come out on the other end before it did not. However, a person like me who stays in front of the computer 10 hours per day immediately knows what is wrong with you and what is wrong with the computer. In this case, there was something which was wrong with the computer. So you can isolate, you can distinguish. It must work. So redo it. Why now it did it and before it did not do it? No explanation. Right. So if you do explain here, and then, okay, you find the percentage of variance explained and then the Biplot. Okay, now let us check the criteria. The criteria is 0.95 to the third. We have to explain at least 0.857. We need at least two components. Otherwise, with one is too little because we explain just something lower than 60%. Therefore, dimension reduction can be done, but is a very mild dimension reduction because it's from 3 to 2. It's not possible from 3 to 1 here because the correlations are very small. Okay, comment. Okay, the exam, do not forget to write the comment. So, first principal component, you explained just a little bit than 60%. So there is 40% of variability which is left out, which is not explained by the first principal component. Okay, then this is, you write what we have just said. Correlations. So when you call PCA-FS and then you put this function, creates in output extract. Extract, you call it whatever you like. You know, generally I prefer to call it out, but call it how you like. This is the struct, and this is the struct which contains all these fields. So our table is the correlation matrix explained. So if there is a capital T, means in table format. So you see the difference between out dot explained and out dot explained T. Okay, much better in table format, goes without saying. So now the correlations. The correlation between variables and principal components are here inside loadings. Loadings or loadings T. So the first principal component is negatively correlated with the thickness and length. Therefore, high values of the first principal components are wafers which have small thickness and small length. Okay? Now, the second variable is mainly correlated with width. Therefore, large values of the second principal components are wafers which have small width, because there is a negative correlation. The other two are much more negligible. Now, what is the sum of squares of the elements of each column? The sum of squares of the element of each column are equal to the eigenvalues. the corresponding eigenvalues, because these are, first column is lambda 1 is, well, I show you. Now I try a different system. Now I try with, as suggested by him, I try with Teams, because the projection wireless screen was losing the connection. So in the matrix, in the loadings, matrix. So here you have square root lambda 1 v1 and square root lambda 2 and v2. This is the loadings matrix. Therefore, the sum of squares of this is what? Lambda 1 v1, lambda 1 v1, lambda 1 v times v1 prime v1 is equal to lambda 1. Okay, lambda 1 is orthogonal, right? And now we compute it. You compute the sum of squares of the jth column. And then you check the sum of squares of the jth column is equal to out dot explained jth element first column or not. Because out dot explained j, this is what comes out from the procedure. These are j explained, right. So is all rows and first column, right. So the sum of squares of the first column is equal to 1.7688. The sum of the squares of the second column is equal to 0.9271. Well, clearly you define the variable j, and then you compute the sum of squares of the jth column, and then you compare it with the eigenvalue, the corresponding eigenvalue. Right. So this is the code, written in the professional way. Do not write 1, write j, then if j is equal to 1, you refer it to the first column. If j is equal to 2, then it is referred to the second column. Right. Eigenvalue, yes. Eigenvalue 2, right. On the other end, before we had eigenvalue 1. Eigenvalue 1 computed. Maybe there is a missing space. Eigenvalue 1 computed. Here there is a missing space. If you want to be fancy and extremely precise, let us see the output. Okay, now the output is very, very nice, with the additional space, so that the users the beginners want to see things in a very neat way. Provide a graphical representation of this correlation, together with the scores, and comment on it. So this Biplot app directly is the direct function which computes the Biplot. Now, let us... so length and thickness have an angle which is very small. Therefore, they are highly correlated. Length and width, they have an angle which, in my opinion, seems to be a little bit higher than 90 degrees. Therefore, very small negative correlation. And, well, width and thickness, here you can find this 90 degrees between the 9 and... Now, let us see the correlation. The correlation of length with the first principal component. Length is negatively correlated with the first principal component. Thickness is negatively correlated with the first principal component. You can see? You can see the loadings. Where are the loadings? Yes. Loadings T. Loadings T, thickness and length. Thickness and length go in the direction of the negative values for the first principal component, so they are negatively correlated. Right. Here there is a wafer which has high length or small length. Here there is a wafer which has high length. This one has high length or small length? This one here. Small, yes, because on the other side, it's on the other side of the arrow. If you compute the angle between this and this, they have an angle which is 180 degrees. Okay, so this is the correlation between row points and column points, but here we show them with points and arrows, but in correspondence analysis, both of them will be shown as points. Here there are, however, points and arrows. Okay, let us do some brushing. Brush, and now we brush this unit here. This unit, here you see, is the one which has the smallest length. Okay? So when you do the brushing, with the brushing, then you can immediately see the characteristics. But this is a thing which is unique. No other software in the world, so far as I know, has implemented it so far. This is our unique technique. Then brushed, you see that you can do even this trick. Right. Now, let us see. Biplot. Compute the commonalities. Compute the commonalities and comment them. Out commonalities. So these are the squares, or sum of squares of the correlations. So therefore, this plus this is the commonality of thickness, that is the proportion of variability of thickness which is explained by the first two principal components. Thickness and length are mainly explained by the first principal component. So their angle with the first is much smaller than the angle with the second. They are mainly, the length has an angle which is mainly orthogonal with the second. Yes, please. Right. Yeah, which has been selected, or the points which are selected. For example, exactly where you show the scatter plot matrix in the original space, right? Because you want to link the information in the Biplot with the information in the original scatter plot matrix. Right. This is a bivariate representation, a synthetic representation, a representation in two dimensions, which should contain, a representative representation of what is in the original space. Right, and this is very nice, the brush, because it enables you to understand what are the characteristics of the units which are brushed. And especially with geographical components, then we are going to see it. If you see that if you hover with the mouse, or mouse over, just for those of you which are much more technical, there is a data tip that is a short explanation of what is that particular checkbox. So you hover on it. So if you find, for example, something that we forgot to put this data tip, please do contact me, because this everything must be explained. What else? Right. Then creates the plots given below. The plots given below, because in the plots given below, if you notice here, there is also the equation of the first principal component. Here there is the equation of the second principal component. And how they are found? They are found using this option, Smart EV chart. Now, I'm going to show you. Okay, so for example, let us see the first principal component. This is the equation of the first principal component. Of course, length, thickness, and width, they are standardized. Now I ask you, it is better to write, I don't know, Z length, Z thickness, or Z width, or it is enough to leave as it is? Because this is something that we were wondering what to show, because the data has been standardized. So this is the standardized version of length, or we thought that it was obvious, so we didn't put Z. However, I don't know. And then look at the different color, then the label, which is as large as the magnitude of the correlation, right? Therefore, you see that width has an effect which is much smaller than that of the other two. And therefore here appears with the label which is very small. Yes, please. Right.
As far as I know, we have like 3 PCAs.
No. 2 PCAs. The PCAs are two. The PCAs are two. The PCA, this is the first principal component, this is the second principal component. Yeah. No, but the first two principal components explain almost 90%, so it is fine. The first two principal components explain a proportion of variability which is very close to 90%, so it is fine. This is a good representation of your three-dimensional space. It is nice because the 3D space you have to rotate. On the other hand, in 2 dimensions, it is fine. You just lose 8%. 8% in statistics is nothing. Okay, for a mathematician, you cannot do it because the data are 3 dimensions and then you pretend to put in 2 dimensions something which has 3 dimensions. Therefore, for a mathematician, something which is horrible, because the data, there is a straight line, either a straight line or there is another function. In statistics, we check for an approximation. Okay, then now interpret the wafers which have large values of PC1 have small length and small thickness. Small length and small thickness. Now, look at the arrow of width. The arrow of width, if you want, is more correlated with the second rather than with the first. You see that the angle here is smaller than the angle here, right? You see? So, is positively correlated with the first, but negatively correlated with the second, because the direction goes down, right? However, width is in between, therefore the communality of width that you can see that is explained by both. On the other hand, length and thickness, the variability is explained here by PC1 and here, well, on the other, yes, more by PC2. Width is much more correlated with PC2 than with PC1. What is the variable which has the largest which has the largest commonality, and width. Variable width is almost perfectly explained by the first two principal components. Okay, now Biplot up with alpha and omega, and so we have to discuss it. We have to discuss now the Biplot and the different representation of the Biplot. Of course, keep in mind, as you said, that the Biplot is valid just if the two principal components explain a proportion of variability which is quite large. Otherwise, there is a certain variability that is unexplained, that is important. Finally, a unit point that is very close to the origin means waffles that have values that are very close to the mean, to the centroid. Points that are very far means points that are distant from the centroid. Moreover, the angle between W6 and width is very small. Can you see it? The angle. Therefore, this means that W6 is characterized by high values of width. Brush, if you do not believe me, W6 brush and W6 width, it has the unit with the largest width. And you can see that the power of statistics. Right, so here you can immediately see what are the units by which variables they are characterized. On the other hand, this W4 is, if you want, in the other opposite direction of the arrow, and therefore it has small values of width. Right. These are all the things about the angle that makes the game. If you have understood the angles, then everything comes out very easily. Okay, this is okay. So the angle of the vector with the axis, we have already commented it. The angles between pairs of vectors has already been commented. And then, well, now we are going to see some algebra. But before doing some algebra, once again, keep into account the angles. Okay, one more time. Right. Okay, now it's this time to do some algebra. Singular value decomposition. So you do this thing. Gamma is equal to gamma star divided by n minus 1, and so this is the thing that you get, U gamma V transpose. Okay, now this gamma singular values of Z, square root of eigenvalues of Z prime, Z divided by N, that is of R, of the correlation matrix, right? So this is, if you want, N times, well, we write, well, in the P or P if the original matrix has rank P or whatever, n times P.
Sir,
Yeah,
is it over n or
n minus 1. N minus 1. Ah, all right, sorry. Correct. Thank you. Sorry, yes, that was a mistake. N minus 1. Right. Yes, absolutely correct. Absolutely correct. Thank you. Yes. Absolutely correct. Okay. Now, Z times V, the matrix of principal components, is U, gamma, V prime, V. So therefore Z times V is equal to this quantity here. Right. Okay, matrix V is orthogonal. What is the covariance matrix of V? Cov this and the cov of this quantity here. So the covariance matrix is V prime ZV divided by n minus 1, V prime R times V prime, and V lambda V prime is equal to lambda, the matrix of the eigenvalues. Okay? So therefore ZV, that is square root of n minus 1 times U gamma, contains the principal components not standardized. So this is the interpretation of square root of n minus 1 U times gamma. And what is U? Right. And now we do it. U gamma V okay, Z V, so is this thing here, right? Then we multiply by gamma to the minus 1. Okay, so therefore matrix U multiplied by square root of n minus 1 contains what? Contains is matrix ZV gamma minus 1. What is the covariance matrix of ZV gamma minus 1? What is this one? The covariance matrix of matrix ZV gamma to the minus 1. Okay, and now we do it. Gamma to the minus 1, V prime, Z prime, Z to the minus 1, V gamma to the minus 1, right? So gamma to the minus 1, so V prime, R, yes, it's the identity, but now we are going to prove it. Gamma to the minus 1, and then here we have V prime, V lambda V to the minus 1, gamma to the minus 1. I wrote everything correctly, I think so. Right, so I'm missing V, this is R, this is R here, okay. Okay, so this is covariance matrix of Z V gamma to the minus 1, gamma to the minus 1 V prime, Z prime, Z V gamma to the minus 1, right? Gamma to the minus 1 V prime R V gamma to the minus 1, gamma to the minus 1 V prime V lambda V to the minus 1. Okay, VR is missing here, right? So this is gamma to the minus 1, lambda, gamma to the minus 1. Gamma to the minus 1 is equal to gamma times gamma, gamma to the minus 1 is equal to the identity. Okay, because lambda is the square of the singular values. Right, and all they are diagonal, eh? Right, therefore, this matrix U, this matrix here, contains the standardized principal components. Right. Now, let us come back. Therefore, if we write first representation of row points, because this thing here can be represented as G times H prime, the product of two matrices. But here there are three matrices. I just write it as the product of two. Therefore, gamma, which is inside here, goes inside G or goes inside H. I put what is in between in matrix G or in matrix H. If gamma, what is here, I put it inside the matrix G or inside the matrix H. Because I write the singular value decomposition as the product of two matrices. Something which represents the rows and the other one which represents the columns. So in two dimensions, they are n times 2 and 2 times p in two dimensions. Therefore, n points in two dimensions, the scores, and then these are the arrows from the origin. Now, G and H. G in this case can be, or G can be this thing here. Therefore, these are the standardized principal components. If G is this guy here, then gamma belongs to H. So it's G times H, the product of three matrices. Okay, so it's G times H. Therefore, this, let me rewrite it. Z U gamma V prime is equal to G times H. Case 1, G is equal U times gamma, and then H prime is equal to V prime. In this case, what is U times gamma? U times gamma, this is the matrix of Z times V. And V is simply the matrix of the eigenvectors. Or, otherwise, if G is U, H is gamma. Let us write it this way, because it is H prime, therefore gamma must become the first. What is G in this case? G is equal to U, and U is the matrix of the standardized principal components. And V times gamma is what? Is the matrix of the loadings. With this representation, then when G is equal to U and H is equal to V times gamma, then you have a representation in which the row points are represented by standardized principal components, and the column points are represented by the loadings. This is representation A. On the other end, second representation, or other, you represent G as Z times V, unstandardized principal components, and H are the eigenvectors. Can you have something which is dynamic? Can you have something that can control dynamically what goes inside the rows and what goes inside the columns? Yes, you introduce the parameters omega and alpha. Look, now representation A is obtained when omega is equal to 1 and alpha is equal to 0. Because if alpha is equal to 0, you have gamma to the 0, okay, the identity, this just becomes U2. And this alpha is equal to 0, so you have gamma V prime. Right? Here you can control omega and then you can control alpha. And now, and this is the thing, this is the bars of omega and alpha on the top. Can you see them? The sliders. So, for example, if omega is equal to 1 and alpha is equal to 0, when omega is equal to 1 and alpha is equal to 0, you represent, and here another thing here, you think it is better to still put omega and alpha or to put the value which is selected by the user? Because in this case, omega is 1, so it should be square root of n minus 1, and then alpha is equal to 0. So in this case, the row points are square root of n minus 1 times u. But here we make it show in the, okay, in this case, look, omega is equal to 1 and alpha is equal to 0. Therefore, row points represent standardized principal components, what I've just shown you. You see in the command line. And then arrows represent the loadings, that is the correlation between the variables and the components. The length of the arrow, the sum of squares of the correlations is the commonality. And so that's the reason why in this case you also plot the unit circle. Because an arrow which has a length close to 1 means that the commonality of that particular variable is close to 1. That is, that particular variable is fully explained by the space of the first two principal components. Therefore, the variable which is best explained is width. On the other hand, if you do alpha is equal to 1, alpha is equal to 1, in this case with alpha is equal to 1, row points represent Z times V, the non-standardized principal components, and the arrows represent simply the eigenvectors. Right. The last one. The last one is this. The last one is this. G is equal to U times gamma, that is Z times V, and the H prime is equal to V prime. Right. So, therefore, it corresponds in this representation to the case where omega is equal to 1, and here you just have V. You just have V. In order to have just V here, alpha must be what? Alpha must be 1, because it's gamma to the 0, then becomes the identity, okay? Right? So if alpha is equal to 1, then here you have U gamma, gamma to the 1, is Z times V, the unstandardized principal components. On the other hand, if I put, this alpha here is equal to 0, then here you have gamma times V prime goes in the column, that is becomes the correlations. And this gamma to the 0 becomes, here gamma to the 0 becomes the identity. Becomes the identity, so you just have U2. What is U2? Matrix. What is matrix U? Matrix U is the matrix of standardized principal components. So the covariance of U, here the covariance of U, the covariance of U, here the covariance of U is equal to the identity. And then we have shown it. Right, so you have seen mathematics, you have seen the algebra, you have seen the computation and the implementation. This closes really the circle. Therefore, here you can decide here the values of alpha and omega as you like. You can do whatever you like. But in the particular cases when omega is equal to 1, alpha is equal to 0, or alpha is equal to 1, you also have the unit circle on top. Therefore, you can do that interactively, or you can call Biplot directly with the parameters omega and alpha. Then compute using a bar plot the score distance of each wafer. So the score distance, then now we are going to see what is the score distance. However, it is a bar of the score distance, something like that. Now we are going to see what is the score distance. Then okay, then you have to show a series of the points in the original space with the three PC axes, all the projection, everything. Here, our function PCA projection does it all. Our function PCA projection actually does everything. So these are the points in the three original space. You see, this is the direction of the largest variability, PC1. You see that the variables, the axes of the principal components that are orthogonal. Then what you find the projection of points along the line of the first principal components. Then what you find the space of the first two principal components. You see that there is quite a lot, and there are units like, for example, W10, that is not very well represented by the space because it has an orthogonal distance, which is large. You see, this is the two-dimensional space and the projection of the points P1 and P2. Now you can see that the projection is orthogonal. Look here. Now here what you find now, this is the yes, the PCA space, correct. This is the PCA space, right. Then you see something like this, but the original space is this one, right. Then you see just the projection in two dimensions, you see. But well, this is the original space. So you want to see this projection is fine. What did we miss here in this two-dimensional projection? Yeah, and then it is determined by the eigenvalues. So now these are the ellipsoid. The ellipsoid, look at the axis of the ellipsoid in the original three-dimensional space. Can you see the ellipsoids and the axis? And the length of the semi-axis is what? Are the singular values. Incredible, eh? There are these dimensions, then the length of the semi-axis are the singular values. The elements of matrix gamma. These are the singular values. The square root of the eigenvalues of the correlation matrix. These are the length of the semi-axis. And in order to compute the volume of ellipsoid, Well, the volume of the ellipsoid, yes, this is the formula for the volume of the ellipsoid in 3 dimensions. A, B, and C, these are the length of the semi-axis, but the length of the semi-axis are the singular values. Okay? And therefore, prod of the singular values, prod of the out dot explained, square root, these are the singular values, the product of the singular values times pi times 4 times, this is the volume of the ellipsoid. Find the length of the second semi-axis, is the second singular value. Find the matrix which provides the best rank 1 approximation of the original matrix. Well, now, or if you want to compute the function PCA res that automatically computes Z hat, the matrix which has rank 1, which is the best rank 1 approximation of the original matrix. Or this is the formula U1 gamma 1 times V1. This is Z hat CHK. Then we check that Z hat and Z hat CHK are the same thing. Now Z hat, what is the rank of Z of this matrix? Z hat. This is a matrix which wants to represent our Z. Right? This has rank 1. If this matrix has rank 1, when you show the points of this matrix, when you have this code, you have the 3D scatter, what do you expect? If this matrix has rank 1, what is your expectation? If this matrix has rank 1, all the points lie on a line. All the points here lie on a line. And here it is. These are the points in the 3D space. They all lie on a line. And in fact, you project them onto this line, in the line of the first principal components. This is what we have just seen. And what is the variance that you lose, the variability of the points that you lose? Compute the sum of squares of the difference with the best rank 1 approximation of the original standardized matrix and divide it by n-1. Compute the here res is equal to the difference between Z and Z hat, which also comes out from MATLAB function PCA res. Well, now what is this quantity here? This is nothing but the sum of the second and the third eigenvalue. Okay? This is the amount of variability that you lose. At the end of the day, the eigenvalues make the game. This thing here is just the sum of the second and third eigenvalue. This quantity here, 1.231, and this is the sum. So you have 3 eigenvalues, out dot explained. Here you have 3 eigenvalues. The sum of the eigenvalues is 3. What you lose if you project the points into the straight line with the largest variability is just the sum of the 2 smallest eigenvalues. Incredible, eh? But that's the advanced algebra that one has to know, because PCA is the basis of everything. Every dimension reduction is based on PCA. Therefore, PCA must be in your language, must be in your background. And then we have the future of the cluster. So you saw that here, when we were projecting things on the first principal, on the first, because this is a space of dimension line, a space of dimension 1, PC1. Okay. Now, let us see now the washers datasets. So there are here a set of washing machines and there are 6 variables. For example, RPM. RPM is how many times this drum rotates, right? So the higher, the better is the result. Energy is energy consumption. Of course, here you want something which is high, but you want to have something which has low energy consumption and maybe maximum laundry capacity, right? Then all the others, price, depth, load, energy, yes. So these are the 6 variables. Now, here, so each point is usually the same thing. Let us go to Teams. This is xi. This is okay. This is the projected points, and this is okay. So the distance here is orthogonal. You want to have orthogonal projection, and this is xi minus xi at. So you have that xi is equal to the distance of projected point in the space of the first k principal components plus the point plus this xi minus xset, that is xi, okay, so the difference between xi minus xi v transpose projected in the space orthogonal to that of the first principal components. So you have this equation here, and then yes, this is 11.14. Well, you can follow them easily, then you can decompose. So the variability of each point can be decomposed into 2 parts. This is referred to every unit. Yes, because a point in the original p-dimensional space, there is the part referred to the projection and the part which is orthogonal. This is the Pythagorean triangle, nothing, okay. This is the sum of these 2 quantities. These 2 quantities here. Therefore, when you take the sum of these quantities, the sum of the first k eigenvalues. So the total variance of the points projected in the space divided by the first k principal components is the sum of the eigenvalues. On the other end, what is the sum of the remaining eigenvalues? The sum is the variability in the space of the points projected into the orthogonal complement of the first k principal components. It's incredible, eh? So therefore, these, once again, the first k eigenvalues, the variance of the points projected. The last p minus k eigenvalues, the variance of the points projected into the space orthogonal to that of the first k principal components. So the variance of this called the score distance, which is nothing but a Mahalanobis distance. So you have the score the score of unit I projected in the space of the first, second case, so you take the sum of the squares, or you write it in this way as a quadratic form, which is the distance of it is just a Mahalanobis distance of each projected point from the centroid. Okay, because the mean is 0, so you subtract 0 from the centroid. And then the orthogonal distance. The orthogonal distance, because as we have seen before, you want to see what are the points whose orthogonal distance is large. You see, for example, the points whose projection that are not very well projected here by the space of the first and second principal component. W10 has a very large orthogonal distance. It is not projected very well. The space of the first two principal components cannot capture the variability of W10 is explained by the third principal component. You see? Therefore, the orthogonal distance in algebraic term is this quantity here. So, in practice, this is, I have implemented everything because a person like me doesn't want to have secrets. What I put on my slides must be something that I've already implemented. Otherwise, I cannot digest things. For me, it's like, it's beyond imagination to be someone who puts on the slides a certain formula that has not previously studied it. Okay, so for example, this is 0.5. 0.5 orthogonal outlier, very large orthogonal distance. On the other end, 0.4. 0.4 is 5, has a very large orthogonal distance, but it is well represented by this subspace. So you want to distinguish between these cases. So you want to have a plot which has the score distance and the orthogonal distance. And then here we have put the labels. The labels come out automatically. This is the outlier map for the washing machine data sets. For example, now let me now do the analysis. Let me go. Let me close this and let me go to MATLAB. So washer. So let me read the data. Washers, PCA, FS, X table, and that's it. Okay, this is automatically the last plot that we have never seen. Score distance and orthogonal distance, right? Now, let us now comment on this data set. Now, variable description. Okay, step 1, standardize. The variables actually have, you can see, here in this case, there is no discussion. There is, the order of magnitude of certain variables is much higher. No discussion, no possibility. Here, the only one possibility is standardized. Okay, compute the correlation matrix. Price and RPM, very high correlation. Yes, you get a better result, but you pay more. And with energy, with what you expect? Well, energy, surprising, is not correlated with price. Let us see, price and energy, minus 0.09. So there are good, very expensive that are very good, or very expensive that are very bad in terms of energy. Okay, SVD, whatever. Then how many components here? 2 components. With the first component, you explained just less than 46%, so 2 components. 2 components, with the first 2 components, you explain 80% of the variability. Correlation. first principal component is a synthetic indicator of price, spin, and speed, and depth. Price, here RPM, and then depth minus 0.84, right? So you see, these are the three variables, price, RPM, and depth, that play the most important part in the first principal component. The second is mainly determined by consumption, energy, and load. Then compute the communalities. The communalities, the variable which is best explained is RPM. And all the variables here are explained quite well. Analysis of the correlation. Therefore, first principal component is negatively correlated with price, RPM, and depth. Angle between price and RPM very small, very high correlation between RPM and so that is these three variables which define the first principal component show a negative correlation with the first principal component. Therefore, I have a variance which is explained very well by the first principal component rather than by the second. The second is mainly correlated with load energy consumption in a positive way. You see the three arrows that goes in the direction of the second principal component. So the first principal component is a synthetic indicator of price, spin, speed, and depth. You see, with minus. You see, therefore high values of the component, therefore low price, low spin speed, low depth. Then, therefore, here you have, on the right, you have low price, low spin speed, low depth. Here, high price, high spin speed, high depth. Similar here, high consumption, high energy, high load. So this is a washing machine that is characterized by high consumption of energy because in the direction of that particular arrow. So, but price and energy, they were not correlated, price and energy. Therefore, the two vectors must have an angle which is close to 90 degrees. But now you can see all the angles. Price, for example, price and consumption. Price and consumption, well, negative correlation. Then here price, therefore these are the expensive washing machine. They're in the direction of high price. Right. Now let us see the geographic principal components. Okay, then, well, what can we do? Okay, you see that now you can see this thing here, color proportional to the orthogonal distance. You see this color proportional. So you can see the units which are badly represented by this orthogonal space, by this subspace. And now, if you now show row names, you can see them. For example, this one is badly represented, but without the colors, you don't know, because this is just a 2D representation. So with the colors, so you can have the information about which unit is best represented. Then, same thing as we have seen below, then with the correlation. Okay, then, for example, okay, we say the price and brush units, and therefore these are the units actually with the generally tend to have high price, you see. Can you see? And then we also forgot to put also this unit here, right, the unit which is in the far left, UT, yes, that was the unit with the largest price. So with brushing, everything is very, very easy. Now, let us see now with PCA geographic. When you load Cities Italy 24, when you load Cities Italy 24, then you can find this user data. Aside properties, user data. Here you have additional information among the user data. And here what did we put? In the user data 1, we put the information about the shape file, the coordinates, the shape of each province. And then in the second, we put just the latitude and longitude. Therefore, now, okay, you supply latitude and longitude. So you apply PCAFS, but now with latitude and longitude. Okay, these 3 lines. Okay. Okay, then you automatically have the bubble plot that is a color of each province which is proportional, the size is proportional to the first principal component. Therefore, the larger is the size, the worse is the province, because as we have seen, the first principal component is correlated with urban fragility, low ISE. Low ISE, I mean poor people, the number of poor people, low ISE. On the other end, the first principal component is negatively correlated with the positive, with the payments in the 30 days, electoral participation very small, quality of life very small, salary small, spending small, employment small, added value small. Therefore, if you have high values of the first principal component, you are in a province which is very poor. Therefore, here in this, where is the plot? Therefore, here, the geobubble, the larger is the bubble, the worse is your province. And the words are here. You see the blue. Okay, now then you can see the outlier map as we have seen before, the loadings, or here if you, well, you must give me other 2 or 3 minutes. If you now do this thing and then smart AV chart is equal to true, so that you also show the eigenvector. So you see, this is very nice, this plot, because it shows the variables which have a negative correlation with the first, which are all positive, all good variables that have a negative correlation with the first. And look at they form here a group. On the other hand, low ISE and urban fragility are just 2 variables. The larger, the worst is. Right? So this is really an indicator of poverty. And that's the equation. You can see the equation on top. With the values ordered in terms of magnitude, from the most important to the least important. You see the elements. Also, if you have suggestion in this plot, now let us see what you get if you have the shape file. The shape file. So if you also supply the shape file, Okay, this is what you get. This is a color which depends on the first principal component. So the red, the worst, the green, the better. Okay, well, fortunately, we are in the here we are in the full green, right? So therefore, and now you want to see, for example, brush units. You see here there are what are the towns which are here? The towns that have, you see, high quality of life, high payment. The towns which are here have really a very good quality of life. But now you can do this, and you can see which are on the map, because we have brushed the units. So when you do the brushing, then automatically the scatter plot matrix appear, and then you can see the units that have been brushed. I don't know if you can appreciate it, but this is something which is unique in the literature, that we have just implemented it. If you find in Python or whatever something which does the same, please let me know. But now we are the only ones who have implemented it with brushing, with interactive brushing. And you see now, the brushed units, the characteristics of the brushed units, they have high deposit. Then you see urban fragility is small. Bankruptcy actually is not so clear about bankruptcy. This means bankruptcy, then, independent of the fact that you are poor or you are rich, you can be dishonest. If you are dishonest, it doesn't depend on richness. You can be dishonest if you are very poor, but dishonest if you are very rich. This does not matter. And this says that clearly that bankruptcy is true for good for rich and poor, but payment on 3D, this is actually, we have the high proportion of payment in 30 days, then high electoral participation, high quality of life, low protest, high salary, high spending, and now you can do brush the units also with, you can remove these brushed units, you see. Okay, so that concludes, well, I would have liked to tell you many more things, however. So therefore, now tomorrow we will do correspondence analysis. And the day after tomorrow, we will see in the computing lab. The file will be shared so that tonight you will have it. Make sure that you subscribe to the GitHub so that you can see when there is a new activity. Okay? Thank you, guys.